So this is our 2025 boat trip project over conquering corrosion in the Galveston Bay Area by Nathan Sun and Greyson Hornes.
Project overview. Our project aims to address the looming issue of corrosion caused by the extremely humid and saline environments present in the Galveston Bay Area. Specifically, we aim to tackle corrosion affecting coastal infrastructure, which people interact with frequently, such as walkways, bridges, and piers. At its core, corrosion is rooted in chemistry. Corrosion is an electrochemical process driven by metals, oxygen, and moisture, especially in coastal environments. Combating it requires a blend of chemical and physical techniques.
So this is our team for this project. We have me, Nathan Sun. I am an aspiring mechanical engineer who is ETAMing in spring of 2026, and I took on the roles of team manager, the project manager, and the research facilitator.
I'm Greyson Hornes, aspiring industrial engineer, ETAMing in spring of 2026, and I'm the team facilitator, project manager, and research facilitator. Challenges we faced choosing a thesis. Initially, we were unsure as a team for which thesis we wanted to develop solutions. We all were seeking different majors and developed differing solutions pertinent to them. Mechanical engineering, industrial engineering. Optimizing marine supply chains, improving container port efficiency, reducing emissions in marine transport, mitigating water pollution from runoff, and preventing coastal infrastructure corrosion. Given the project's focus on developing chemistry-based solutions for ocean-related challenges, we chose to address the widespread issue of corrosion in coastal infrastructure due to substantial evidence discovered during our boat trip.
So these are the images that we took from our boat trip. So we visited the Pelican Island Causeway Bridge, the SS Selma shipwreck, the Texas City Dike, the Gulf Copper Shipyard, and the Coast Guard Station, which we unfortunately couldn't get to because of a block in the boat trip route. So the two photos that we believed best supported our thesis were the photos from the Gulf Copper Shipyard and the Pelican Island Causeway Bridge. And this was because there was visible degradation and corrosion in the photographs. And as you can see from both of them, there's corrosion occurring not just at the waterline, but also way above the waterline. And this is important because above the waterline, there's a lot of infrastructure in which people interact with. And if these pieces of infrastructure are corroded away, they can present a great danger and a great risk to the people working on them and interacting with them frequently day by day. Such as the bridge, the supporting beams are being corroded, and the sea spray reaches the underside of the bridge, and this is what causes the corrosion of these supporting beams under the bridge. In the Gulf Copper Shipyard, as you can see, there are walkways, there are elements of infrastructure that are higher up above the waterline, but they are still being corroded because of this sea spray and humidity. So this is what we wanted to address and fix. And further, our research corroborates our claim that corrosion is heavily affecting not just the Galveston Bay area, but around the United States as well. So a 2024 City of Galveston report indicated that increased repair costs due to humidity and salinity from corrosion occurred. A Galveston beach house collapsed from corroded fasteners holding the house in place, killing a woman, and corrosion caused a dock collapse in Georgia, killing 7 people. And we found that these alternative solutions to mitigating corrosion were quite ineffective in our case, because one of the methods, which was impressed current cathodic protection, which is a method of preventing corrosion by sending electrical currents through the protected infrastructure, actually was found to weaken the metal by cracking it instead of actually protecting it. And cathodic protection, which is the sacrificial anode method of protecting against corrosion, is also insufficient alone against high humidity and sea spray. A research paper found that these protective methods often work well when submerged underwater, but does not work well with infrastructure that is above the waterline. And one of the main reasons why sacrificial anodes work better underwater is that when underwater, sacrificial anodes work more efficiently due to water being a greater conductor and facilitator of electron movement and electron flow through the material. But when sacrificial anodes are exposed to air, electrons have a much more difficult time moving through the metal, thus making sacrificial anodes less efficient in protecting against infrastructure when above the waterline.
Addressing corrosion in marine infrastructure. How it is addressed scientifically by material science, environmental science, and corrosion engineering. It affects marine life, mixed effects on marine life, negative effects on marine life, with harmful pollutants being released into waterways. Can also be beneficial to a degree by providing new areas for marine life to thrive. How should engineers mitigate this problem? Implement durable materials, regularly inspect and maintain infrastructure, and implement preventative technologies. It is near impossible to reverse damages.
So our solution that we devised for this problem was a sort of corrosion-resistant shield that acts as a protective barrier to salt spray, and it doubles as a sacrificial anode protection against saline conditions. So this shield acts as a sort of first layer protection system. As you can see on the diagrams to the right, it is meant to be connected to these points of infrastructure where the fasteners, the pieces of these holding the infrastructure up and supporting it, it aims to protect this using a corrosion resistant material such as galvanized steel, 400 series stainless steel, aluminum, cheap, lightweight, low cost materials that are financially efficient as well as efficient against protecting against corrosion. It acts as a first layer protection system and implements sacrificial anodes to hinder oxidation at humid conditions. And it is much easier and cheaper to implement than the aforementioned impressed current cathodic protection system because it doesn't require constant maintenance. It doesn't require constant monitoring. It's a passive system, which means it does not need to be monitored 24/7. It works by itself. It is cost effective because it utilizes low cost corrosion resistant alloys such as 400 series stainless steel, aluminum, galvanized steel, nickel based alloys. These materials are known to be very cheap and easy to work with, which is why we chose these for our shield. And this solution is easier to retrofit on existing structures. As you can see on the right, it can be attached to bridges, walkways, infrastructure that people frequently interact with. And this solution combines the benefits of sacrificial anodes and implements some of the benefits of the impressed current cathodic protection by protecting a system that is above the waterline without having to be constantly monitored, which is why we believe this solution is a better alternative to currently existing solutions already in place. And these were our references that we used for this project. And thank you for listening to our presentation, and I hope you have a good day.